When Ben Franklin died, he left a lot of money to the city of Boston. His plan was for them to loan that out to students, and they would charge some interest. That would help his endowment stay current with inflation and hopefully grow a little bit over time. So we could ask, how much should this money have grown if it was really lent out at 5% interest and everybody paid back? How much should it have grown in 100 years with first just simple yearly compounding, and then we could ask, what if we compound infinitely often? What will happen in that case? So remember, with yearly compounding, we're thinking if we want to know how much we have at year t, we could take how much we had the year before and multiply it by 1, because we would get our principal back, plus we would get 0.05 times our principal as our interest payment. So this is just saying, well, the amount you have at the end of year t is the amount you started with plus 5% of the amount that you started with. Now we could peel this back one more, because the amount you had 2 years ago, or the amount you had 1 year ago would be the amount you had 2 years ago times 1 plus 0.05, and that's getting multiplied by another 1.05. And then this, the amount you had 2 years ago, is the amount you had 3 years ago times 1.05 times these two 1.05, so 1.05 cubed. You can see however many years we go back, we just have to raise 1 plus 0.05 to that number of years. So we get a to the t. If we peel it back t steps, we'll be back to the a at time 0, what we initially started with, times 1 plus 0.05 to the t. Now, the amount we start with in money, we usually call that the principal. So we have the amount of money at any future time is going to be the principal times 1 plus 0.05 to the t. Or in general, if it's yearly compounding, you're going to have the principal times 1 plus the interest rate, written as a decimal there, to the t. Good. So that would be yearly compounding. Now, with continuous compounding, the formula that we get is that we're going to say, well, if we do continuous compounding, then the amount I have at some time h later minus the amount I had at a sub t. So in some short period of time, we should take our 0.05, right? That would be yearly, so we're going to multiply that by h, which is a fraction of a year, a small bit of a year, probably, and then multiply that. So this is the yearly interest rate times how much of the year has elapsed times how much money we have in the bank. So this would be if we compounded every h. What I'm going to do here is divide both sides by h, so I'll have 0.05a. Now with continuous compounding, what we do is we compound infinitely often. So this h, the time between compoundings, is going to be going to 0. So we're going to take the limit as h tends to 0 of that. And of course, that's the definition of the derivative. So we have dA dt on the left equals 0.05a. Now you recognize this as a problem that we've already solved, right? Anytime you have to solve d quantity dt is proportional to the quantity, you know that this is the solution. You get it by separation of variables. So looking at this, we have r is 0.05 and a and y are the same thing, so we know the solution is going to be a at time t equals a naught e to the 0.05 t. So, okay, but of course we a naught, since this is money, we usually call that the principal. I'll use p here. And you recognize this is our compound interest equation. You've probably seen it before. You just didn't realize you could get it by solving a differential equation. Okay, let's look in both cases now. If it was compounding each year for 100 years, we'd have the principal, which is 1,000 pounds, and then we'd have 1.05 to the 100. On the other hand, if it was continuous compounding, we should get more because we're earning interest on the interest sooner in this case, e to the 0.05 times t. In this case, t is 100 years. Let's calculate what those two numbers are, or just get an approximation anyway to those two numbers. So in the first case, I'm going to take 1.05 and raise that to the power of 100. and then I'll take that 131. So we're going to get 131 times what we started with. So if I multiply that by, we started with 1,000 pounds here, so then the amount's going to be 131,501.26. 131,501.26 pounds sterling here. On the other hand, if it was continuous compounding, we should make even more than that, because we get to earn interest on the interest. So take your 0.05 and multiply that by the number of years, which is 100. We get 5. Now I'll take e to that number. We get 148 times however much we started with. So instead of 131 times the amount, we get 148 times the amount. So if I multiply that by our initial 1,000 pounds, we'll have 148,413.16. So what was it? 148,413.16 pounds sterling. So that would be pretty good growth there. So let's see, in 100 years, it actually only grew to 90,000 pounds. So for whatever reason, either they couldn't get the 5% interest rate, or people weren't paying back like they should have, so it didn't grow quite as rapidly. If you have a few people maybe default or something on those loans, that could happen. So what continuously compounded rate was that? So let's assume that they got some constant rate over time, sort of an average rate. We know that dA dt should be equal to the rate times a, and we know the solution of that differential equation is the amount is a naught e to the rt, or in money terms, a naught, the initial amount of money, is usually called the principal. So, well, we know the principal was 1,000, and we know that they waited, or if we waited 100 years, that the money turned out to be 90,000. So we can solve this equation. If we divide both sides by 1,000, 90,000 divided by 1,000 is 90, equals e to the r times 100. We're trying to figure out what would be the average rate then if we think about it as continuous compounding. So I'm going to take the natural log of both sides, and the natural log of e to the 100r would just be 100r. So the interest rate would be the natural log of 90 over 100. And let's figure out what that is approximately by using a calculator. So I'm going to take 90 and find the natural log of that value, and then divide that by 100, and I get 0.0449. Okay, so 0.045 basically. 0.045, that is 4.5%. So they didn't do too bad. They almost hit the 5% value that Ben Franklin required.